Okay, so let's move on. I'm going to move you, Audric, because I haven't used the... I think that's going to get the board for you. Oh, the indices?
Yeah. So
like over here?
Yeah. Oh, thanks. Let's see. 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, and 1. Yeah. I think that's all.
Cool.
Thanks.
No problem. Lemma 4.9. Lie algebra. We have A. L is nilpotent. Then any Lie subalgebra of L is nilpotent. And B, if L mod the center of L is nilpotent, then L is nilpotent. So again, this lemma is really, it's anchored in exercise 4.1. All right, so I think if there was a problem I would recommend working here, Audric, it would be 4.1. I think that's really the glue that holds things together here. So, all right. He says, what? He says A is basically he's like A is obvious. All right, that always makes me nervous. When he says something's obvious, will it be obvious to us if we actually try to prove it, right? So you got a subalgebra. Let's just think about it here, proof. I'm going to say, I'm not going to use an L sub 1 for the sub. There's too many indices floating around here already. Let's use a different letter. Like, I don't know, K. K, a subalgebra of L. All right. Then, yes, K1 is a subset of L1. We argued that before because L1 is L parentheses 1, right? We argued this before in the previous lemma. All right, and well, let's see here. We have K, let me use a different letter, J, right, is equal to the product of L with K, J minus 1. So I think, the argument goes something like this is clearly a subset of what? L with L J minus 1, right? My bad. I should put a what here? Not L, but K. Yeah, thank you. But I think this is reasonable. I mean, certainly K is a subset of L, and you can prove that this is a subset of that by arguments similar to the ones I've made earlier today. So then what? So then if L is nilpotent, right? This is equal to what? This is equal to Lj, right? So if L is nilpotent, that means that there exists some M such that the mth, lower central series terminates to 0. And if that's 0, this is 0. Therefore, any Lie subalgebra is nilpotent. It really is clear. It's clear as long as you can convince yourself of this inclusion here, which I do believe is true. Now, part B probably requires a wee bit more thinking, right? So, okay. How about for part B? If L mod ZL is nilpotent. So what he does is, I think he uses his exercise. It looked like he was using exercise 4.1 again, if I remember right. Let's see here. He says, by induction or a variation of exercise 4.1, you can show that L mod the center of L, all right, the kth power of that, if you will, is equal to the kth power of L plus Z of L mod Z of L. All right, so in other words, it is so this is basically, this is a lemma. Prove this, okay? If you want to understand the proof here better, prove that, all right? But that can be shown. And once you have that, what does it get you? So if L mod ZL is nilpotent, right? So if L mod ZL to the M is equal to 0, then that's equal to L to the M, right? Plus the center of the L over the center of L. What's that mean? For that to be the 0 coset, that means that Lm has to be a subset of the center of L. So L is nilpotent. All right. Now, if Lm is a subset of the center of L, what's that tell you? How about Lm plus 1? See, that would be L with Lm, right? Yeah. But if it's contained in the center of the Lie algebra, that means the bracket of anything with it is 0. That's what it means to be the center. So if Lm is in the center of the algebra, then this is 0, which then proves that L is nilpotent as charged. Ooh. And then he has a warning. The analog of lemma 4.4b does not hold. If I is an ideal of a Lie algebra L, it is possible that both L mod I and I are nilpotent, but L is not. Ooh. So caution. Can have L mod I and I nilpotent, yet L not nilpotent. And the example apparently is given by that two-dimensional non-abelian Lie algebra that was discovered in the previous chapter. All right, so finally the time has come today to talk about simple Lie algebras. All right. So I think I can erase this bit here. And I'll move you back, Audric, in just a second.
I'm still copying. That's fine.
Cool. Well, you're copying, I'm writing then. Definition. Definition. The Lie algebra L is simple. All right, simple. If it has no ideals. All right, other than 0 and L and is non-abelian. Making it non-abelian is a convenience. All right. Now you're ready? Excellent. Ooh, I see you have a Texas mathematics shirt.
Yes. I have a Notre Dame one too, so it means that.
It means you went to Notre Dame. I think it's what it means. Hey, I didn't get a free t-shirt at my visiting weekend. It's not cool.
That much. You're already there.
Let's see here. So this is a Lie algebra is simple if it has no ideals other than 0 and L. Let me read the preamble to that definition. He says, the previous section suggests that we might have a chance to understand all finite dimensional Lie algebras. The radical of L of any Lie algebra is solvable. L mod the radical is semi-simple. So to understand L, it's necessary to understand what does an arbitrary solvable Lie algebra look like? What does an arbitrary semi-simple Lie algebra look like? And if we're working over the complex numbers, the answer to 1 was found by Lie, who proved in essence that every solvable Lie algebra appears as a subalgebra of the Lie algebras of upper triangular matrices. So the solvable Lie algebras essentially are they're sort of abstract versions of upper triangular matrices. And then he says we'll give a precise statement of Lie's theorem in section 6.4. And then for 2, an arbitrary semi-simple Lie algebra, we can show that every semi-simple Lie algebra is in fact the direct sum of simple Lie algebras. So this is a simple algebra has no ideals other than 0 in itself, and it's non-abelian. He says the restriction that a simple Lie algebra may not be abelian removes only the one-dimensional abelian Lie algebra, but without this restriction the Lie algebra would be simple but not semi-simple, and we don't want that. So we need to find all the simple Lie algebras over the complex numbers. He says this is a major theorem. The proof is based on the work of Killing, Engel, Cartan, and will eventually prove most of the following theorem. So here's the theorem. Simple Lie algebras. With 5 exceptions. With 5 exceptions. Every finite dimensional Lie algebra over the complex numbers is isomorphic to one of the classical Lie algebras. What are those? Well, SLN, C, SON, C, and SPN, 2N rather, C. These are the Lie algebras respectively of the special linear group, the special orthogonal group, and the symplectic group that we talked about when I started this semi-course, half course, whatever. Full course for you, Audric, full course. You're doing the homework, right?
Yeah.
Okay. And the 5 exceptional Lie algebras are known as, they've got names.
This is the homework that Bill gave me, right?
Yep. Yeah, this is, you have the first 4 Bill homeworks. I will add to that eventually. E6, E7, E8, F4, and G2. And then he says we've already introduced the family of special linear algebras, right? And so he gives the definition of the symplectic Lie algebras here, because I think that's the one he hasn't done yet. All right. So, but I think we did it. Maybe not. Maybe we didn't. Let me see how I am on time. Oof. Well, I better stop there, but I mean, on page 33, let me just talk, I want to talk a little bit, it's rather than spinning my wheel, we could write the definition up there, whatever. These are, we'll talk more about these, okay? But I want to talk more just about the language here, nilpotent and solvable. There's also this kind of decomposition for a matrix, like just regular linear algebra. You can break any matrix up into sort of like a nilpotent piece and well, I forget what the name of the other piece is actually, now that I think about it. But the other piece is diagonalizable. So, well, there's how can I say this? The Jordan form, right? For for the kth Jordan block like this, lambda, it's got lambdas down the diagonal, and it's got ones on the super diagonal in my notation typically. All right. So what you're looking at is lambda times the k by k identity, right? Plus this other matrix, which I'll just call n sub k. What happens when you take n sub k and raise it to the power of k? Well, you get 0. Let me show you specifically how this works. Like n3, 0, 1, 1, 0, 0, 0, 0, 0, 0. All right? n3 squared, 0, 0, 1, 0, 0, 0, 0, 0, 0. n3 cubed, 0. So the Jordan block also has this sort of decomposition into a diagonal piece and a nilpotent piece. But here we're not talking about something funny like a derived series or something, right? We're just literally talking about the power of it eventually is 0. So I'm just saying the use of this word nilpotent, it also has application in the study of linear algebra. And we can ask questions about like what's the nilpotent piece of a matrix. It's a reasonable thing to think about. If there is no nilpotent piece of the matrix, it's diagonalizable, I think is something you could say. But anyway, I'm being fuzzy here, but what I wanted to say is that this term nilpotent is not native to Lie algebras. It's a more general, there's nilpotent groups, there's nilpotency is a more general concept. The other thing I wanted to say is that, so Lie found this classification theorem. I think there were some mistakes in his work. I want to say it was, I think it was Killing. One of these guys came through and just did everything in detail and just nailed it to the ground, nailed it to the wall, really did it well. Found all the errors or oversights, sins of omission, let's say, in Lie's work, something like that. And so by the early, before World War I, these things were all pretty well pinned down and known, classified. Much later, in the 1970s or so, the super analog of this, like super Lie algebras. So instead of just having a commutator, you have a graded bracket where you also have an anti-commutator. So the even operators, they satisfy something like AB plus BA. And so you have a graded Jacobi identity, all these things. These were classified about 50 years ago now, something like that. And then that, in turn, led to a study of deeper things called vertex operator algebras. The vertex operator algebras are things like they have to do with the set of symmetries on a circle, something like that. It gives you something called the Virasoro algebra. The Virasoro algebra is like the first example of a vertex operator algebra. But these are infinite dimensional analogs of a Lie algebra. So this is the start of a story which is still playing out in terms of classifying interesting algebraic structures that are like Lie algebras, let's say. And also, I think there has still been work done in the last 50 years on these kinds of questions over other fields, like fields of characteristic 4 or something like that. If I remember right, my brother said those were done, I don't know, like 40 years ago, something like that. The other thing Bill told me, which I thought was interesting, I'd pass on to you guys, is, I told you that the terminology solvable Lie algebra came from solvable Lie group. I believe that the study of, what Bill was saying was that the study of nilpotent groups, it flowed the other way. Like people started looking at nilpotent Lie algebras and properties of nilpotent Lie algebras, and then they went back and asked the question, so what can we say about correspondingly nilpotent Lie groups? So like the direction of discovery flowed the other way. Like, so these are, analogous structures, right? There's some sort of functor which takes you from Lie algebras to Lie groups. If you study category theory, you can make that more precise. It's one of like the big examples of, a functor between different categories of math, if you will.
Can you quickly say why Lie algebras has so much to do with rigid transformations at first?
Why do Lie algebras have so much to do with rigid transformations? Well, we saw, this is the SONC, that's the Lie algebra of rotations, right?
Exactly, yeah.
So I guess that's part of why it come up in the study of transformation groups, right? Like these questions were originally motivated by studying groups of continuous transformations, coordinate transformations, if you will, on the equations of mathematical physics. And so that's naturally tied into the question of rotations. So I guess it comes up in...
Going over physics, it's still one of the biggest problems I've heard is coordinate transformations. Is this supposed to be a generalization of coordinate transformation stuff?
Oh, the problem of understanding general... the question of what is the...
GR and stuff like that.
Yeah, right. I hear people say things about the trouble of, infinite dimensional Lie groups. What's the group of symmetries for a manifold? And I think it's such a big question that we don't always have an answer to it. It's what are all possible coordinate transformations for a manifold? we can limit our focus to coordinate transformations which are related in some sort of manageable way to a coordinate system we already have. That's not too bad, right? Like you have one coordinate system, you can consider all the other coordinate systems which are related, in a sort of orthonormal sense, right? Like you have,
yeah, just by like shifting this, like by theta, yeah.
right? So like, we have Lorentz transformations. They take us from one inertial frame of reference to all other inertial frames of reference. But yeah, we do think about general coordinate transformations in general relativity, don't we? And so there are,
That's what I was wondering.
yeah.
This
I don't,
obviously this was studied before, but like
yeah.
how we use this today, I feel like this makes a lot of sense to be used today.
I'm sure there are more things to say here for sure. Like I know, I'm pretty sure that this G2 is the, that is, that's come up in string theory and M theory, these G2 manifolds or whatever. What are they called, G2? All of these exceptional Lie algebras come up in weird places. Like especially in string theory, there's, E8 heterotic string theory. I think that may be the group corresponding to this exceptional Lie algebra, for example. There are some, these are, it's not an isolated story. Anytime you're looking at, something that has this sort of structure and you ask what are the possibilities, well, these are the possibilities. So, you're going to run into them. What, of course, is interesting is the study of simple groups, right? Of finite simple groups. A finite simple group is what? It's one which has no normal subgroups other than 0 in itself, right? Well, the identity in itself. So there's no non-trivial proper subgroups. No non-trivial normal subgroups, which means it has no interesting quotients, right? So the study of simple groups was only completed, what, in like the 80s. So that was, there's like the proof of all simple groups is like 10,000 pages long or something stupid. But we have a complete catalog of all possible finite simple groups. What's that? You said what?
They didn't like award anything. They didn't award anything to those people because there was so many people working on it. Right?
There's too many people working on it for an award. Yeah, well, I think there's different pieces of it that have gotten different, awards and things, I suppose. I mean, there's this Feit-Thompson result in it, like the Feit-Thompson, F-E-I-T Thompson. The proof of that is like 250 pages. And that's just like one of the cogs in this machine of the proof of the finite simple groups. And I think like the last one, it's this, was it the group of automorphisms of the monster group or something? There's this, this guy, he calculated it a couple years ahead of the computers. It was just a feat of like stupendous arithmetic. And it was kind of silly because he could have just waited 2 years. Everyone understood Moore's law. The computers were going to calculate it. Anyway, there's whole books that have been written about all this stuff. So, I don't know. It's pretty neat. Like, there's not a lot of other fields of study you can study that you get these kind of theorems where you find out, like, what are all the possible different kinds of paintings that you can draw of a particular type. Like, we can tell you, these are the ones. There's no other paintings to draw of this type. That's it. That's it for the art. What's that?
In another context, I guess.
Yeah.
That's a similar question I'm trying to answer in another context. But yeah, I mean, those are the most beautiful theorems, like classification, geometry theorems.
Yeah. The more you know. But all right, well, I think I'm going to stop it here for today. And so next time we'll pick up in chapter 5. I think I'm relatively happy with what we've done for chapter 4. So thanks, guys.